G'day, great to be here. Yeah, it's great to represent BG&E here in Boston and to pick up the prize. It's a real honour. I hope you guys can understand me. The accent's not too strong, you know. Yeah, okay, cool. So I'm going to go through the presentation. There's some references to metric system, but I'll try to convert to inches where I can. We'll see how we go. So I'll give you some background on the project. A few things I want to talk about, the sustainability aspects, the construction sequencing, structural design, differential movements, column shortening, temporary works, and the monitoring that we did. It's really I guess, a project of collaboration, QQT. It was a $1 billion development, and it was made possible by combining the heritage sites next door, the airspace over those into the 50 Bridge Street Tower and extending the tower to effectively double the floor space. So this slide is it's like one of those late night diet commercial advertisements. You got here the old tower on the left, and then you take a few pills and away you go. You got the one on the right. Yeah, if only it was that easy. The one on the left was a 1970s building. It was 46 stories tall. The one on the right, 51 stories, and 70% of that building has been retained into this building here. So again, I'll walk you through the 4 easy steps for transformation. You got the original building, 1976. The red is the demolished portion of the tower. In grey, you've got what remained, and then the blue is the new tower, and it's barely recognisable from its current form, from its original form. The floor plate. The existing tower had a square floor plate. It was fairly regular. There was a central core and a ring of in situ beams around the outside. The slabs were 4-inch precast and with a 2-inch lightweight topping. And the right is the new structure, which we've added on a core just onto the north. It's stitched on the core, extended the floor plate with steel and composite metal deck flooring. The columns are CFT concrete filled tubes, and you can also see there's an atrium void which enables the different tenancy floors to interconnect through a staircase. Some of the key project stats. So the building, 215 metres tall. Lettable area is increased from 45,000 to 90,000 square metres. The existing walls were strengthened with steel plates and carbon fibre, and then the hanging twisted floor plates are supported from an inclined CFT column that runs the whole way from basement 4 up to level 51, and then hangs each of the blocks from that one inclined column. The team for the project, BVN and 3XN, collaborated to do the architecture. 3XN were the executive architect out of Denmark, and BVN did most of the documentation. The contractor was Multiplex, and my firm BG&E, we did the structural materials and the construction engineering. One of the really cool things about this project is the sustainability. So we achieved 12,000 tonnes of carbon saving by reusing the existing structure. This is something that now the City of London are looking at as a pilot in how to reuse their existing building stock and apply the same type of principles to getting the most out of the existing structures. I guess from the contractor's point of view, they saved $140 million by doing this, and they also saved 13 months from the construction sequence. I'll just walk you through the construction sequence quickly. So this is just a high-level diagram. We produce many more diagrams, I guess, for the contractor, but this kind of gives a good overview. So we demolished the basement structures on the left of the building that were existing, and took them down to B4 and took it down another level down to B5. We cut a slot in the existing building to fast track the new core construction. We started then to build the new core up through the existing structure as it was simultaneously coming down. And then we started a jump structure here on the last image, which was built from the B5 basement up to level 14, where we transitioned, and the demolition got down to level 12, the new structure got up to level 14, and then we crossed over and we kept on going up with the new structure, and then came back and infilled below with the floors to tie it all back together. So just have a look at, I've got a video, have a look at, you can see the jump structure. So this was a time lapse. I think this one was played last night. It was 3 years into a minute. At the time, it was the largest scaffold project in the Southern Hemisphere. And you can see the demo starting to come down from the top, and the jump structure coming up on the left, down the bottom there. And then they overlap about here, and that's where you start to go up as full floor plates, and then it gets filled in down the bottom. You can see a section of facade was left out as well. This was to allow for the differential shortening between the existing structure and the new structure. Going back to the body transformation analogy, we had to do an initial health check on the building. So we had to, jump on the scales, measure the skin folds, see where we stood at the start before we started, doing any design or construction. And to accurately predict the behaviour, we took 1,600 core samples. And this was the key to reducing the amount of demolition and the amount of strengthening on the project. You can see around here, level 20 to level 30, we actually achieved results that were below the design strength on the original documentation. So we had to go and refine our testing. We took more cores. We went back and we were able to reduce the strengthening significantly by taking more cores, isolating the strengthening to certain parts of the building, and that saved the client a lot of money and time in demolition and rebuild. Okay, so these tested values, we put them into our nonlinear finite element model, and that produced the staged construction. So we started the model 1970 is when the time started to apply to the concrete, and we allowed it to creep and shrink, and then the new construction to start. And you can see the change in the centre of gravity of the building as it gets built. It starts to move originally it goes back to the south, and then it comes back to the north. So I'll just demonstrate these. This is what we charted based on the ETABS modelling. So that's where we started. We moved back 50 mils to the south, then 200 mils to the north, and then we moved a further 50 mils to the north, taking into account the time-dependent properties of concrete and the creep and shrinkage over the design life. You can also see on the photo on the right the inclined column and the load paths where you get the tie floors, and they're inducing an overturning effect on the whole building. So we carbon fibre strengthened up the back face where you've got that tension force, and that overturning effect due to gravity load is what causes the additional 50 mil movement there over the design life. And obviously there's just the wind load as well that adds to the deformations. One of the techniques applied to limit the overturning effect was a pore strip to separate the new concrete from the old concrete. These were filled after 42 days with a special high modulus concrete mix. Another way that we accounted for the differential movements of the two buildings was to preset the columns. So from our model, we determined where we needed to build the new structure, enable it to adjust and come down over time to meet with the existing building. That was a large challenge throughout the project, trying to effectively predict where things would end up over time. Temporary work. So one of the biggest construction challenges was the temporary works. As you can see in the photos, we were required to prop and brace throughout the building for the demolition, and we also had to prop and brace the new structure, the jump structure, as we built that up because it wasn't connected to the cores. The loading on the columns as well was continuously changing. We undertook strain compatibility checks on all the temporary works, and we had to constantly evaluate the lateral restraints to buckling as these were changing as slabs were either demolished or new slabs were added. So our structural documentation had to have very detailed construction sequencing to enable the builder to execute the project. So for your building, just like your body in transformation project, it's important to measure it as you go. So we set up a health monitoring system on the project for two main reasons. First reason was to get the feedback and update our model, and the second reason was as a warning tool. Just so if something did start to go off course, we could correct it before it went too far and pose a risk to safety. So I had tilt sensors monitoring rotation of walls, accelerometers to measure damping frequency and mode shapes, strain gauges to model the connection of the new core to the old core, and we also had a plumb bob that was essentially a piano wire with a 5 kg mass down the bottom that we put in one of the old lift shafts throughout the construction, and that was a way to measure the effect of gravity on the and the centre of mass changing throughout the construction. It was a very accurate, actually, way of measuring how the building was behaving over a period of time. That's it.